Hello, hello, hello. Good evening, all. I am Saurabh, and I welcome you to this live session for the course Applied Thermodynamics. In previous few sessions, we have been discussing some basic concepts related to internal combustion engines. In today's session, we will continue our discussion on IC engines, and we will try to solve some problems, which I hope will be helpful for you to solve the assignment problems. Okay, so let us begin with our first question. The question number one, it says that the Otto cycle is the air standard cycle of CI engine, air standard cycle of SI engine, or vapor power cycle of CI engine, or power cycle of SI engine. So I hope you can easily answer this question. The last two options, like, you can discard, because the CI engine or SI engine, uh, they are not the vapor power cycles, right? So we have to tell that Otto cycle is the air standard cycle for which engine? CI engine. CI engine means compression ignition engine or diesel engine, or it is the air standard cycle for the SI engine or spark, like a spark ignition engine or petrol engine. Sometimes we say. So I I hope you know about the air standard cycles. These are the simplified cycles, standard cycles for the thermodynamic analysis of these engines, CI engine or SI engine, because the real cycle, the real process going on in these engines, that is very, very complicated, and the analysis of those real processes is very, very difficult. Okay. Uh, for example, there are a lot of different gases are there, fuel is there, combustion is happening, and everything is changing with respect to time. Okay, the properties are changing, the thermodynamic properties of different gases are changing because of the temperature changes or the pressure changes, and the concentration of different species is changing. So the real and the analysis of real process is very, very difficult. So for the simplification, what we do, we assume some air standard cycles. Okay, so there are some air standard cycle for CI engine, some are for SI engine. So we have to tell that Otto cycle is air standard cycle for which engine. So this is very easy question, and I hope you must have guessed that the correct option should be the B part. The Otto cycle is the air standard for spark ignition engines. Okay, or sometimes we can say gasoline engines. Gasoline, basically petrol. Okay, so the engines used in your motorcycle, the bike, so they are SI engine. Okay, and the air standard cycle for SI engine is the Otto cycle. Okay, if I try to make a PV diagram for Otto cycle, it will look something like this. This is our PV diagram. First there will be a adiabatic or isentropic compression. Then at constant volume, there will be heat addition. Okay. Then there will be adiabatic expansion. Okay. And then again, there will be constant volume heat rejection. Okay. So 1 to 2, this is compression, asymptotic compression. 2 to 3 is basically heat addition due to combustion. But in air standard cycle, we don't we assume that there is no combustion, but there is heat addition. Okay, because combustion means there are different gases. But in air standard cycle, we assume that there is air is the only working medium, and it is an ideal gas. And 3 to 4 is our power stroke, and 4 to 1 is the uh, exhaust stroke. Okay, heat rejection. Okay, so this is the Otto cycle. Okay, so here we can see that heat addition takes place at constant volume. Okay, so basically what happens in a gasoline cycle, a gasoline engine or SI engine, is that uh, mixture of air and fuel comes inside the cylinder, and it is compressed, it becomes very hot, and with the help of spark plug, it is ignited. Okay, then combustion take place. And in air standard cycle, this combustion is at constant volume. Okay, so I hope this is clear, and we can move to the next question. Question number 2, it says that which of the following has the highest cetane number? So you must have studied that cetane number is a very important property for which engines? For CI engines, compression ignition engines. Okay. The fuels which have higher cetane number, they can be easily auto ignited, and the fuels which have lower cetane number, they cannot be easily ignited. So the fuel which is to be used in a CI engine or diesel engine, that should have a higher cetane number. Okay, so diesel has a higher cetane number. Okay, so I'm sorry. Okay, so fuels for CI engines should have a higher cetane number, so that they can be easily ignited. And the petrol or petrol-like fuels, they have lower cetane number. Okay, so for this reason, uh, the fuels which are good for SI engine, they cannot be used in CI engine because they have very low cetane number. For example, the alcohols, the methanol or ethanol, they can be easily used in SI engines. They can be used in spark plug engines, but they cannot be easily used in diesel engine, because if you try to use them in the CI engines, they will not be auto ignited. Okay, so then you will have to use some ignition improver or something which can initiate the ignition. Okay, but anyways, among these fuels, which has the highest cetane number? The correct option is option A, heptane. And heptane has the highest cetane number. Okay. Can you please tell the chemical formula of heptane? It is C7. Okay. C7 and H. How many H? 2n plus 2, right? 17 into 2 plus 2. So it should be 16. Okay. So similarly, you can write it for hexane. It should be C6 plus H14. And for butane, it will be C4 H10, and pentane it will be C6H12. Okay, so this C7H16 has the highest cetane number among these fuels. Okay, so this is a good CI engine fuel. And If diesel is to be used in CI engine, then why we discuss about heptane or other these hydrocarbons? The reason is that these are compounds, okay, and the compounds has well-known properties. Diesel is not a compound; it is a mixture of many compounds. So when you want to do the analysis of diesel combustion, then there are a lot of products, okay, because diesel contains a lot of compounds, and this compound will uh, behave differently. They have different properties. So what we do, we take some reference fuels, okay, which have well-known properties. So heptane is a compound and it has fixed properties. So if you want to study the combustion of a CI engine, then you should use some reference fuels. Okay, so heptane is a very good reference fuel for diesel. Okay, uh, and if you want to have little more involved analysis, then you can use few more compounds, heptane or C10, like that. Okay, anyways, so these things are used when you do CFD, okay, computational fluid dynamics of engines. Okay, anyway, I hope this is clear that heptane has the highest C10 number, and C10 number is a property for CI engine fuels. Okay, so I hope we can move to the next question. Question number 3. It says that the process of inducting pressurized air in the engine cylinder is called as turbulence or supercharging or preignition or both turbulence and supercharging. Okay, let's try to understand the question first. We know that during the intake stroke, the air or air fuel mixture in the case of CI engine, SI engine, and air in the case of CI engine, that is inducted into the cylinder. How it is inducted? Because the piston is going down. Okay, so piston is going down, so it is creating some sort of vacuum. Okay, so it is reducing the pressure inside the cylinder, and the pressure outside the cylinder is atmospheric pressure. Okay, so when the pressure inside the cylinder becomes lower than the atmospheric pressure, so the air comes inside. Okay, and when the piston is at BDC, then this cylinder is completely filled with the air. Okay, so whatever the volume of the cylinder is and whatever the density of atmospheric is air is, so that much air you can take inside the cylinder without any special technique. Okay, and you also know that if you want more power, you will have to burn more fuel, and if you want to burn more fuel, then you will need more air, right? But since the volume of this cylinder is constant, so there is restriction on the volume of air or the mass of air. Okay, but if you want more air, then what you can do is you can send the pressurized air or the compressed air inside the cylinder, right? Because the compressed air will have more density, so you will have more air inside the cylinder and you can burn more fuel and you can get more power. Okay, so the cylinder, so the engine which was like 100 cc, that can behave like 120 cc or maybe 150 cc. Okay, so this technique is called supercharging or turbocharging. Okay, so the turbulence, it has nothing to do with the pressurized air or whatever turbulence. You must have studied in fluid mechanics. Okay, the supercharging is the correct option. Pre-ignition, no, it is not the correct option. It is a bad thing in CI engines. Okay, both turbulence and supercharging, this is also not the correct option. Supercharging is the correct option. Okay, so turbocharging or supercharging, these are the boosting techniques. Boosting means you are sending compressed air inside the cylinder, okay, which has more density. Okay, so what is the difference between turbocharging and supercharging? To compress the air, you will need a compressor, right? And how that compressor is being run, from where it is getting energy, that is the difference between turbocharging and supercharging. In the turbocharging, that compressor is run by a turbine, and that turbine is run by exhaust gases which are coming from the exhaust of the engine. The gases which are coming from the exhaust of engine, they have a lot of energy, they have heat content. Okay, from that heat content you can run a turbine, and you can connect the shaft of that turbine to the compressor, and from that compressor you can get the compressed air, and that air can be sent to the this cylinder. And in between you will have to also use a intercooler, because when you compress the air it becomes hot, and hot air will have less density. Okay, so if you can cool the compressed air, then it will have more density anyways. And the so you can see that turbocharger is not using the energy that is produced by the engine. It is using the energy of exhaust gases, which are anyway will be wasted if you don't use the energy of exhaust gases. But in supercharger, what happens, uh, the the compressor is getting energy from the engine shaft. Okay, so basically it is like a getting energy from the engine power, whatever power is being produced by the engine. So with the that shaft it is connected compressor of supercharger, and then it works. Okay, so in supercharger you have better control because it is directly connected with the engine shaft. And in the turbocharger you have little less control, because you have to wait for the change in exhaust gases, and then that change will reflect in your turbocharging equipments. So there is a little turbo lag. And in supercharger there is no lag, but it is consuming your energy output of the engine. But anyways, both of these are boosting techniques to compress the air. Okay, so part B is the correct option. If there would have been one more option, turbocharging, that would also have been the correct option. Okay, so I hope this is clear, and we can move to the next question. Question number 4, it says that an engine indicator diagram is used to determine speed or mean effective pressure or indicated horsepower, or both MEP or indicated horsepower. So what is an indicated diagram? You know what is an indicated diagram? Indicated diagram is a diagram which is produced by indicator. Okay, and what is an indicator? uh, in older engines, in older research engines, I should say, there used to be a special device which used to plot a PV diagram. Okay, so in engines there used to be an indicator. In indicator there was basically a stylus and some paper, and this stylus will move according to the change in pressure and volume, and that stylus will mark something, will plot some graph on the paper, basically a PV graph. Okay, so since that graph was plotted by indicator, so this is called indicator diagram. Okay, so the PV diagram is basically indicated diagram. Okay, so nothing special. Okay, so from PV diagram, what can you get? Can you get the speed? No, you cannot get the speed because there's no time information in the PV diagram, right? So you cannot get the speed. You can get the mean effective pressure. Yes, you can get the mean effective pressure. Mean effective pressure is basically some sort of average that you can get from this PV diagram. Okay, so mean effective pressure you can get from this diagram. Indicated horsepower. Yes, power you can get because from PV diagram you can get the information about the work output. Okay, so both of these should be correct. So basically the D part should be the correct option, both MEP or this ISP. Okay, so I think this is clear, and we can move to the next question. Question number 5. It says compression ratio of an internal combustion engine, IC engine, is what? So there are 4 options. First option says the ratio of volumes of air in cylinder before compression stroke and after compression stroke. Part B says volume displaced by piston per stroke and clearance volume in the cylinder. Part C says the ratio of pressure after compression and before compression. And last part says swept volume to the cylinder volume. So if you have watched the lectures properly, then you should be able to answer this question. We will see all these options one by one. So basically, compression ratio is the ratio of maximum cylinder volume to the minimum cylinder volume. Okay, compression ratio is maximum cylinder volume to the minimum cylinder volume. So when you will get the maximum cylinder volume, when piston will be at BTDC, right? Bottom dead center. Okay, volume at BTDC. And when you will get the minimum cylinder volume, when the piston will be at the TDC. Sorry, it is BDC, bottom dead center. So this is at BDC, bottom dead center, and this is at the TDC. Okay, this is at the TDC. So when piston is at TDC, you will get the minimum volume that sometimes we call clearance volume. Okay. And when piston is at BDC, we'll get the maximum volume. Okay. Anyways, so let us see all the options one by one. Option A, the ratio of volumes of air in the cylinder before compression. So before compression means volume at bottom dead center. And after compression, it will be volume at TDC. Okay. So yes, this is the definition of compression ratio. So option A is correct, but we will also check the other options. Part B says volume displaced by piston per stroke and clearance volume in the cylinder. Uh, no, it is not the correct option because volume displaced will be what? Sorry. Displaced volume or swept volume sometimes we say. It is maximum volume or volume at BDC minus volume at TDC. Okay, so this volume, I mean, when piston travels from BDC to the TDC, so whatever volume it swept, that is the volume displaced. Okay, so this is not the correct option. Okay, so part B is not the correct option. Part C says the ratio of pressure after compression and before compression. No, well, compression ratio has it is related to volume, not the pressure. Okay, you can make a relation between volume and pressure, but you need to check which type of processes are taking place. Okay, and part D says swept volume to the cylinder volume. This is also not the correct option. Okay, cylinder volume is the volume at the BDC, maximum volume. Okay, so anyways, I hope this is clear that part A is the correct option. Compression ratio of engine is the ratio of volume of air in the cylinder before compression, that is the cylinder volume, total cylinder volume, to the air to the volume of air after compression. Okay, that is clearance volume. Okay, so I hope this is clear, and we can move to the next question. Okay, question number 6. It says, what is the formula for compression ratio of Otto cycle? Compression ratio is compression ratio. Okay, doesn't matter for which type of cycle it is. It is same for Otto cycle as well as any other cycle. Okay, so whatever we have discussed in the previous question, so that should be perfectly valid for this question. Okay, so compression ratio we have discussed. Compression ratio doesn't matter whether it is CI engine or SI engine. It is same. Okay, so let us check all these options one by one. Option A says volume of cylinder at the beginning of compression. Yes, sorry, 2, the volume of cylinder at the end of compression. Correct. Okay, because the volume of cylinder at the beginning of the compression, it is the maximum volume or the cylinder volume, and the volume of the cylinder at the end of compression, this is the clearance volume. Okay, and this is what is the definition of CR, or the compression ratio. So option A is the correct option. And we should also check the other parts. uh, Part B says that RK is the volume of cylinder at the end of compression to the volume of cylinder at the beginning of cylinder. No, it is just, reciprocal of this, reverse of this. So part B is not the correct option. Part C says the volume of cylinder at the end of compression to the clearance volume. No, this is basically one. Okay, this is one, because the volume of cylinder at the end of compression, this is clearance volume. Okay, so no, this is not the compression ratio. Both of these quantities are equal. So this thing will become one, and one is not the compression ratio. And part D says none of the above. So part A is the correct option. Okay. So this is very important quantity, compression ratio, because it affects the efficiency of any engine, whether it is CI engine or SI engine. Efficiency of engines depend on compression ratio. Usually the higher compression ratio gives the more efficiency. So you try to increase the efficiency, but you cannot keep on increasing the efficiency. There are some constraints, because when you increase the compression ratio, then near the compression stroke or TDC, the temperature of pressure becomes very very high, and because of very very high temperature and pressure, there are some problems, like, right, knocking, so. And because of high pressure, the cylinder should be able to sustain the high pressure. So you need to make it stronger, and when you make it stronger, you need to put more mass of the metal, so engine will become heavy. So usually diesel engines are heavier than the CI engines, because diesel engines have higher compression ratios, so they need to be, you know little more stronger, so they are heavier, bulkier. But so I hope this is clear. Okay. So we will move to the question number 7. So if you have any doubt, you can just raise the hand, or you can just write your doubt in the comment section, or you can unmute yourself and ask. If you have no doubt, then it's great. Question number 7. It says diesel cycle is also known as, again, 4 parts. Part A says constant volume cycle, constant pressure cycle, constant temperature cycle, or none of the above. So if you know the diesel cycle, you know the PV diagram of diesel cycle, then you can easily answer this question. So if you can write the answer in the comment section, it will be great. Or otherwise, I will make the PV diagram. Okay. For the diesel cycle. This is pressure, this is volume. So, uh, first there will be an isentropic compression. Then what? I should make it little, something like this. Okay. This is isentropic compression. Then heat addition at constant pressure or constant volume. In SI engine, it was at constant volume. Okay. In the previous question, I think it was question number 1. We have seen that in CI engine, there is constant volume heat addition. Heat addition take place at constant volume in SI engine. But in CI engine or diesel engine, the heat addition take place at what? Constant pressure. Okay. Okay. So constant pressure heat addition. Then there will be power stroke, that is basically isentropic expansion. Then, we have constant volume heat rejection, or the exhaust stroke. Okay. Sorry. It is 4. So this is our diesel cycle. Okay, 1 to 2, it is isentropic compression. 2 to 3, it is constant pressure heat addition, and 3 to 4, it is again isentropic expansion, and 4 to 1, it is constant volume or isoporic, heat rejection or exhaust. Okay, so now you can answer this question. Diesel cycle is known as constant volume cycle? No. So basically, we have to tell that which type of process is there during the heat addition. So heat addition, you can see from 2 to 3, it is constant pressure. Okay. So option A, constant volume. No, it is not the correct option. Part B, constant pressure cycle. Yes, because heat addition is taking place at constant pressure. Part C, constant temperature cycle. No, and none of the above. Obviously, not correct. So, uh, so part B is the correct option. I hope it is clear. Sorry. And if it was asked that Otto cycle is also known as, then which option would have been correct? It would have been constant volume cycle. Okay, but for diesel cycle, it is constant pressure cycle. Basically, we have to tell that heat addition take place at either constant pressure or constant volume. Okay, so if it is clear, then we should move to the question number 8. Okay. Okay. Question number 8, again diesel engine. So question number 8 says a diesel engine has a compression ratio of 16. Yes, diesel engines have higher compression ratios, 16, 17, or even higher. The fuel cutoff takes place at 6% of the stroke. Then fuel cutoff ratio is what? So again, we should make the PV diagram. You should try to solve it by yourself as well. And if you can find the correct option, then you should write in the chat box. Anyways, the same diagram, okay? From 1 to 2, it is sorry. Excuse me for my drawing. It is isentropic compression. Then 2 to 3, constant pressure heat addition. Then 3 to 4, isentropic expansion or the power stroke. Then 4 to 1, it is exhaust, okay, or constant volume heat rejection. Okay, so you should be clear about some basic terms. Okay, so compression ratio, what is compression ratio? We have discussed in previous questions. Compression ratio is the ratio of maximum volume to the minimum volume. So maximum volume is at 0.1 or 0.4. Okay, so and the minimum volume is at 0.2. Okay, so if I make these boundaries, so this is a minimum volume and this is maximum volume. So this ratio of V1 to V2, this is our compression ratio. Okay, let us see, let us write it R. Okay, and there is something called cutoff ratio. Cutoff ratio is basically the ratio of volume after the combustion and before the combustion. Okay, before, so it is after the combustion the volume is will be what? Combustion is ending at 0.3. Okay, so after the combustion volume is V3 and before combustion starts it was V2. Okay, so V3 by V2, this is our cutoff ratio. Let us write it as RC. Okay, so this is cutoff ratio. So I hope the terms are clear. Now we can try to solve the question. A diesel engine has a compression ratio of 16, so R is given to be 16, and fuel cutoff takes place at 6% of the stroke. Okay, which stroke? This is full stroke from point 2 to 4. Okay, this whole, expansion. Okay, from 2 to 4. 2 to 4, this is expansion. 2 to 3, it was heat addition, and 3 to 4, it was asymptotic expansion, but 2 to 4 is the whole stroke, expansion stroke. Okay, so what it is saying that cutoff takes place at 6% of the stroke. So 6% of the stroke means maybe you can add some new paper. 6% of stroke means 6 by 100 V4 minus V2. Okay, so at this point cutoff take place. So point 3, let us, here it is cutoff. Anyways, so it is at 6% of the stroke. Okay, so we have to tell the cutoff ratio, and cutoff ratio is V3 by V2. Okay, so can we tell the V3 by V2? It's simple, mathematics. We can also write this as V1 minus V2. Okay, and from compression ratio, what we have? We have V1 is equal to 16 V2, right? So 6 by 100, and V1 is equal to 16 V2 minus V2. Okay, is equal to 6 by 100, 15 V2. So this is what? Uh, this is V3 minus V2. Okay, this part. Okay, this black part is V3 minus V2, and this is 6% of V4 minus V2, or 6% of V1 minus V2. Okay, so now it is very easy to solve this question. Just divide both side by V2. So what will we get? V3 minus V2 minus 1 is equal to 6 by 100 into 15. So this is the quantity V3 by V2. This is the quantity we have to find. Okay, this is a cutoff ratio. Okay, so cutoff ratio will be equal to 15 into 6 divided by 100 minus 1. So just calculate this value. Had we made some mistake? We are getting something wrong.
Sir, it is +1.
Huh?
Isn't it +1?
Oh, sorry. Right, right. So what should be the correct? I mean, so it should be 0.9 plus 1. So it should be 1.9, right?
Yes.
So which part should be the correct option? Part B, right? 1.9. Okay. So I think it is clear. So if you have no doubt, then we can move to the next question. Should we? Okay, we will solve question number 9. Okay, question number 9 says the firing order in an IC engine depends on. Before moving forward, I will just explain what does it mean. Uh, in multi-cylinder engines, like most of the engines will have more than one cylinder. Like in tractors or buses or heavy-duty, applications, you will have more than one cylinder, two cylinders or three cylinder or even four, five, or engines. Sorry, many cylinders. So they cylinders are not fired simultaneously. Okay, so there is some order. So maybe first cylinder, there will be firing in first cylinder first, or second cylinder then maybe some other cylinder. So in which order they are being fired, so that is what is meant by firing order. Okay, so this is very important, that in which order these cylinders should be fired. Why it is important? Like, if you fire all the cylinders simultaneously, then there will be a huge jerk. Okay, so there will be a huge vibration. Okay, so that is not favorable, that we don't want. Okay, so what we do, we fire these cylinders, these engines, in such a order that vibrations are minimum. Okay, or the noise is minimum, so that there is very less damage and very less noise. Okay, so this firing order will depend on what? So we have to tell this. So option A says cylinder arrangement. So cylinder arrangement basically means that in which orientation cylinders are arranged. Okay, for example, cylinders can be all the cylinders can be in one direction. Okay, so all these cylinders are in the same direction, and this is connected to the same shaft. Okay, crank shaft. Okay, and there can be something like this: one cylinder is in this direction, another cylinder is in this direction, and they are connected to shaft like this. Okay, they are in opposite direction. uh, Another possibility can be some other orientation. There is something called V type of cylinder. Okay, so there are a lot of arrangement, different arrangements. Okay, and all these arrangements are made to basically optimize these vibrations. Okay, so this is what is meant by cylinder arrangement. Okay, and part B is crankshaft design. So you know what is crankshaft? Crankshaft is basically this shaft. Uh, this is, let us say, our cylinder, and this connecting rod, and this is connected to this crankshaft. So crankshaft is basically something like this. Okay, so from here the cylinder will be connected with the connecting shaft. So crank basically means something which is not straight. Crank means ill or sick. But anyways, so crankshaft basically is not the straight shaft, so it is crankshaft. So crankshaft design. Part C says number of cylinders. So all these factors will affect the vibrations. And in order to optimize the vibrations or the noise or the stress developed in the crankshaft, the firing order will have to optimize. So the firing order will depend on all these factors: cylinder arrangement, as well as crankshaft design, as well as the number of cylinders. Okay. So the correct option should be part D. Okay. So I hope this is clear. We can move to the next question, question 10. Okay. Question 10 says A vehicle powered by a spark ignition engine, okay, great, follows air standard Otto cycle with gamma is equal to 1.4. So gamma is basically ratio of specific heats Cp by Cv, and it is given 1.4. The engine generates 16 kilowatt of power while consuming 8 kilogram per hour of fuel. Okay, this is fuel consumption rate. The calorific value of fuel is 42 megajoule per kg, and we have to tell what is the compression ratio. Okay, okay. So you have fuel consumption rate, or you can, using the fuel consumption rate and the calorific value of fuel, you can find what is the energy input or the chemical energy input you are providing to the engine. Okay, so what will be that value? Let us write it as q in. Okay, so it will be equal to mass flow rate into the calorific value of the fuel. So it is 8 kilogram per hour multiplied by 42 megajoule per kg. So it will be 42 into 8 megajoule per hour, or 42 into 8 divided by 36002 megajoule per second, or megawatt you can say. Okay, or if you multiply this thing by thousand, so you will get kilowatt. 42 into 8 by 3600 into 1000 kilowatt. Okay, so this is energy input, and how much power is being produced or the work output. This is 16 kilowatt. Okay, so you can find the efficiency. Efficiency will be equal to work output or the power production rate divided by energy input rate. Okay, from here you can calculate. And for Otto cycle, you know the formula for efficiency. What is that for Otto cycle? It is 1 minus 1 by r to the power gamma minus 1, right? R is compression ratio. Please correct me if I'm making any mistake. And R is given here to be 16. I'm sorry, R we have to find. Gamma is given 1.4. So neta from this formula we will find as 1 minus 1 divided by r to the power 1.4 minus 1. And from here we can find this value, and we can just compare, and we can find the r. So this is equal to 42 into 8 divided by 3.6. So from here we can find the r. So 1 by r to the power 0.4 is equal to 1 minus this thing. Okay, so r will be equal to 1. Okay, so you can just find this value. Maybe I don't know this calculator will support or not. Maybe I will use another calculator. Probably we have made some mistake, some negative values are coming. So again, we will have to check this. Yes, this efficiency value we have put it wrong. Okay, 16 we have left. So from here we can find the efficiency. It will come out to be 16 divided by 42 into 8 divided by 3.6. So it will come out to be, let us calculate this value first. 42 into 8 divided by 3.6. So it is coming 0.642. Okay, efficiency from here it is coming 0.642. So 0.642. 1 minus 0.642 will be equal to 1 upon r to the power 0.4. So r will be equal to 1 minus 1 upon 1 minus 0.642 to the power 0.4. Okay. So so I'm getting it something around 13 point something compression ratio. So if you are getting some other value, then just let me know. But let us check the options. 9.6 or 11.4 or 13.1 or 15.2. We are getting 13.04. So part C is the closest option. Okay. So maybe we can select this one. 13.1. We are getting how much? 13.04. Okay. I hope this is clear. We just need to remember the formula for efficiency of Otto cycle. Okay. Sometimes these formulas are, difficult to remember, but at least form you should remember that if you increase the compression ratio, then what will happen? If you increase the gamma, then what will happen? At least these type of things you should, remember. You don't need to memorize this, you just need to understand this. Okay, because many times in exams or some other places, it can be asked that if you change the compression ratio, then how it will affect the efficiency or something like this. So if it is clear, then we will move to the question number 11. Question number 11 says the compression ratio of a gas power plant cycle corresponding to maximum work output for the given temperature limits of T min and T max will be some blank space. Here gamma is the specific heat ratio of air. Okay, till now we have been discussing Otto cycle or diesel cycle, but here it is gas power plant cycle. So if you have studied gas power plant cycle, then I hope you know about gas power plant cycle. This basically works on Breton cycle. Okay. So if I make a TS diagram for Breton cycle, there is isentropic expansion. This is TS diagram. Then isobaric expansion. Then again isentropic process. And then again isobaric process. So there are two isobaric processes and two isentropic processes. 1, 2, 3, 4. So from 2 to 3, you are getting work output. Anyways, the compression ratio. Okay, so here also the definition for the compression ratio is same. The maximum volume to the minimum volume. Okay, if I make a PV diagram, it will look something like this. So compression ratio is defined as ratio of maximum volume to the minimum volume. Okay. So let us try to solve this question. This is saying to produce maximum work output. If you try to write the expression for the work output for this cycle, then you can write it as work output or net work. This will be equal to mass flow rate Cp T3 minus T2 minus mCp T4 minus T1. Okay, this will be the net work output. And for the maximum network output, this quantity has to be maximized. Okay. And here the maximum temperature is at 0.3. This is T max. And minimum temperature is at 0.1. This is T min. So we should try to write all the expressions in terms of T2, sorry, T3 and T1. Okay, as much as possible. So we should rearrange this thing. mCp, you can write T3 minus T4, mCp and T2 minus T1. Okay. And also you can write mCp. You can take T3 common and it will become 1 minus T4 by T3 minus mCp. Just take T1 outside. So it will become m T2 by T1 minus 1. Okay, like this. Now what we have? We have T min and T max and gamma we have. Okay, gamma is specific heat ratio. 2 to 3, sorry, 1 to 2, it is isentropic compression. So you can use the relation for isentropic, expansion on compression, adiabatic process. Okay. So for adiabatic, PV is equal to PV to the power gamma is equal to constant. In terms of temperature, if you want to write, you want to remove the pressure. And one more thing we should note it here, that P2 is equal to P4, sorry, P3, because it is isobaric process, and P4 is equal to P1. Okay. If you want to write in terms of temperature, then it will PV is equal to nRT. So if you want to remove this pressure thing, then it will become T into V to the power how much? Gamma minus 1 is equal to constant. Okay. So you can write T P1 V1 to the power gamma minus 1 is equal to T2 V2 gamma minus 1. So what you have is okay, just write like this. Similarly, So from here, what you can write is P223, it is isobaric process, and 421, this is also isobaric process. And for a isobaric process, what we can write is that volume is proportional to temperature. Okay. So P2 by T3 is equal to P2 by P3. And T4 by, sorry, what is this? This is T3. T3 by T4 is equal to P3 by P4. Okay. Sorry. This should be volume, right? Because for constant pressure, it is proportional to volume. So V2, V3, and V3, V4. Correct? Correct. And what else we have? Okay, these quantities we have. And we have to maximize this quantity. Okay. Hello? Am I still connected? Okay. Now, what is the compression ratio? Compression ratio is the ratio of maximum volume to the minimum volume. Okay. So where is the maximum volume and minimum volumes? Before the start of isobaric compression, we have minimum volume. Okay. Before the start of isobaric compression, we have minimum volume. And at the starting of isobaric compression, this is 0.1, this is 2, 3, 4. Okay. 1 to 2 is isentropic compression. 2 to 3 is isobaric expansion, and so on. Okay. So what we have? We have, okay, sorry, we have to find what? We have to find the compression ratio. So compression ratio will be, R will be what? It will be V4 divided by V2. This quantity we have to find. Okay. So we have a lot of information. Just we will substitute all these things in expression for W. So Maybe from here we can get some information. T3 by T4, okay, fine. And T2 by T3, we also need to find T2 by T1. And what it will be? T2 by T1. This is isentropic process. So we can write V1 V1 to the power gamma is equal to P2 V to the power gamma, or from PV is equal to nRT. You can write these things in terms of temperature. So it will be T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. Okay, so you will get T1 by T2, sorry, T2 by T1 is equal to V2 by V1 1 minus gamma. Okay, so we will substitute all these values in the expression for work output. That is not working. Okay, we'll write it again. MCP, let us, instead of MCP, let us write K. Okay, so K is basically MCP. This is constant. So K into T3 in bracket 1 minus T4 by T3 minus T1 T2 by T1 minus 1. Okay, so this is W. Okay, now we'll substitute all these values. What is fixed here? Here, T3 and T1 is fixed because minimum and maximum temperature is fixed. Okay, so we can, instead of T3, we can write T max. Okay, and instead of T1, we can write T min. This is our expression for W. From here, you can write a T max 1 minus P3 by P4 T min V2 by P1 1 to the power gamma. Now you can differentiate this equation with respect to R. Okay, but before differentiating, you will have to write all these volumes in terms of R. Okay, then what you will do? You will do differentiation of W with respect to R and make it 0. Okay, then whatever expression you will get, from there you will find R. Okay, and that will be corresponding compression ratio for which you will get the maximum work. Okay, so maybe it can be little lengthy. So for the time being, we can skip. If we get time, then we will return to the question. Okay, but before completing this question, we should, I mean, look other questions as well. Otherwise, these questions will be left unattended. Okay. So question number 12, it says the number of working stroke per minute for two-stroke engine is the twice the speed of engine in RPM. So do you understand this question? So there are mainly two types of engine, two-stroke engines and four-stroke engines. So four-stroke engines are now more popular. More popular. Most of the vehicles have four-stroke engine. Two-stroke engines used to be, I mean, they were being used in some scooters or some, older vehicle, but they had some inbuilt advantages like lightweight and others. So for these good properties, they can make a good comeback. For example, in your, uh, lawn movers, the grass cutters, those who work on, petrol engine, they were basically two-stroke engines. They were light, but they were not giving that much, fuel efficiency. So now we have shifted to four-stroke engines. So what is the difference between two-stroke and four-stroke? That for one complete cycle means four steps: compression, combustion, expansion, and exhaust. So all these steps, if they happens in four strokes, one stroke means when piston moves from one dead center to another dead center. For example, if piston moves from top dead center to the bottom dead center, then we say it is one stroke. Or if it moves from bottom dead center to the top dead center, then also we say it is one stroke. Okay. So number of these reciprocations, they are basically strokes. So number of strokes per cycle, they are basically two-stroke or four-stroke. So that is what we mean by two-stroke engine or four-stroke engine. So in four-stroke engine, to complete one cycle, piston will have to go four times up and down. Okay. So two times it will go up, two times it will go down. Okay. And when you know that when piston will go up and it will come back, then your shaft will rotate once. Okay, from point 1 to 2 it has gone up. Okay, so this is half the rotation, and from 2 to 1 again it will come back, then it will be another stroke and the cycle will be completed. Okay, sorry, so one revolution means two strokes. Okay, so in four stroke engines or one complete cycles, there have to be four strokes, right? And four stroke means two revolutions, right? Because per revolution there are two strokes. And similarly, in two stroke engine, there has to be two stroke in one cycle, and two stroke means one revolution. Okay. So in two stroke engine, one complete cycle take place in one revolution. In four stroke engines, one complete cycle takes place in two revolutions. Okay. So now we will return to the question and try to answer this. The number of working strokes per minute for a two-stroke engine is the twice of the speed of engine in RPM. RPM basically is revolutions per minute. Okay. So is this correct option? That is false, right? Because for every one revolution, there is one cycle. Okay. So working cycle means, working stroke means uh, power stroke. Okay. Or any type of stroke. Okay, so basically it means that for one revolution, how many cycles are there? So for one revolution, there are one cycle for two strokes. And for four stroke engines, for one revolution, there will be half cycle. Okay, so this is question is for how many? It is for two stroke engine. So for this question, one revolution is equal to one cycle. So this is false. Okay, so I hope it makes sense. So if it's clear, then we will move to the question number 13. Okay. Question number 13 says the air standard thermal efficiency for diesel cycle is higher than Otto cycle. So this is the same say an incomplete question. There should be mentioned something else as well. Let us write or same compression ratio. Okay, now it is correct. Okay, so for same compression ratio, the air standard thermal efficiency of diesel cycle is higher than Otto cycle. We have to tell whether it is true or false. So if you know the formula for efficiency of both these cycles, then you can actually answer this question. For Otto cycle, it was 1 minus 1 divided by r to the power k minus 1, correct? We have written it somewhere in some question here, okay? So k is basically gamma. Okay, let us write it gamma r to the power gamma minus 1. This is for Otto cycle. So similarly, there is expression for efficiency of diesel cycle. So what is that? For diesel cycle, it is 1 minus r to the power. I will try to make r and gamma a little different so there is no confusion. Okay, so the first few steps are same, but there is something else for diesel engine. RC, RC is basically cutoff ratio. We have discussed cutoff ratio in some previous question. Gamma minus 1 divided by gamma RC minus 1. So this is the formula for efficiency of diesel engine. So for same compression ratio, R is same. Now we have to compare this neta for Otto and diesel. So in diesel, this term is extra term, and you have to tell that whether this term is more than one or less than one. If this term is more than one, then you are removing something extra from this term. Okay, if this term is more than one, then efficiency of diesel engine will be less as compared to efficiency of Otto cycle for the same compression ratio. If it is less than one, then it will be more. Now this question is more like a mathematical question instead of a thermodynamic question. Okay, so this will be less than one or greater than one. This we have to find. Gamma is more than one. Okay, RC, this is also more than one. Now you can find. This quantity is will be greater than one. So either we should prove this, or maybe this can be left as an exercise for you. I will encourage you to plot this thing, or maybe I can try, but if time is left, then we will plot this thing and we will see how this quantity varies when this RC and gamma varies. Okay, maybe we should try it now, or let us see how it varies. Is there any graphing thing? What we had to plot? Okay, let us say RC. Instead of RC, we will write X, and instead of gamma, we will write just gamma or some other constant. Okay, so X to the power R, not R, gamma. Instead of gamma, let us make something G. Okay, minus 1 divided by G into X minus 1. Okay, now we can add the slider for gamma, and we know that G is always greater than 1. So we will just vary this thing. Okay, now you can see. Okay, so when it is 0, gamma is 0, then it is undefined because G is in the denominator. And as we increase the G slowly, you can see that this value is and what else we need to keep in mind that this X is greater than 1. X means this RC. RC means cutoff ratio. This is greater than 1. So we have to check this graph uh, on the right hand side of 1. Okay. Okay. Maybe I will just write X is equal to X is greater than, not equal to, X is greater than 1. Okay. So in this region, in the green shaded region. Okay. So in the green shaded region, you can see that this value for this quantity of the first expression, this is always greater than 1. Okay, when we make it 0 or just greater than 0, then when we make G equal to 1, then it is 1. Okay, but we know that G is basically gamma. It is always greater than 1. It is the ratio of specific heats, Cp by Cv. Okay, it is always greater than 1. So when you make it greater than 1, then you see that this quantity which is written here in the this bracket, so this is greater than 1. Okay, but I will encourage you to do this thing mathematically instead of graphing. So this thing is greater than 1, and you are subtracting this thing from here. Okay, so this was the first term was the efficiency for you know auto cycle, and you are reducing something extra, so this whole term will be reduced. Okay, so the neta for auto will be more than neta for diesel. Okay, why? Because gamma is greater than 1, and RC, this is also greater than 1. Okay. Now I have one more question for you. What will happen for the limiting case? Limiting case means when RC, the cutoff ratio, is equal to 1, then what will happen? Should we try this as well? Maybe we can. For RC is equal to 1, what will happen? Just we will see the quantity in the bracket. So R to the power gamma minus 1, gamma RC minus 1. So you can see that when you put RC is equal to 1, then you will get 0 by 0 type of, something. So that is, undefined, but you can find the limit. Okay. Limit RC tends to 1. Then can you solve this limit? Now, this is not the question of thermodynamics. This is a question of mathematics. Okay. And if you have read the limits, then, when it is 0 by 0 form, then sometimes you can use L'Hospital or whatever you call that, L'Hospital sometimes. We cannot do the justice to the name of that great mathematician, but anyway, whatever you call, we can just differentiate both side with respect to RC. So when you differentiate the numerator, it will become gamma into RC to the power gamma minus 1 divided by gamma into 1. Okay, so when you put RC is equal to 1, you just cancel out gamma. When you put RC is equal to 1, so it will be 1 by 1. Okay, so for limiting case, this value will be 1. Okay, so when RC is equal to 1, then efficiency of diesel cycle and Otto cycle are same. Uh, okay, anyways, so I hope this is clear. You just need to keep this formula in your mind, and if you cannot remember the formula, then I request please remember at least the form. Okay, if you reduce the RC, what will happen? If you uh, change the cutoff ratio, then what will happen? If you change the gamma, what will happen? Okay, and a good way to remember all these things is to just look at the plots. Okay, because pictures are easy to to keep in mind. Okay, the more information can be grasped by images, pictures. Okay, so I hope this was clear. So we will just quickly try to solve this question. Question number 13. In dual cycle, heat addition takes place in at constant volume. Part B says first at constant volume, then at constant pressure. Part C says constant pressure, and D says none of the above. So dual cycle is something like in between diesel cycle and Otto cycle. Okay, so in Otto cycle, heat addition take place at constant volume, and diesel cycle heat addition take place at constant pressure. In dual cycle, heat addition take place at both at constant pressure as well as at constant volume. So does the constant volume heat addition take place first, or constant pressure heat addition take place first? So we will make the PV diagram, and it will become clear. Okay. First there is isentropic compression, then constant volume heat addition, then constant pressure heat addition, then isentropic expansion. These are not very smooth curves. I am sorry for my drawing. Anyway, so just okay. So 1 to 2 is isentropic compression. 2 to 3 it is constant volume heat addition, and 3 to 4 it is constant pressure heat addition, and 4 to 1 it is isentropic expansion. Sorry, 4 to 5 is isentropic expansion, and 5 to 1 is um, constant volume heat rejection or exhaust. Okay, so Heat addition take place at first at constant volume, then at constant pressure. Okay, so now you can easily answer this question. Okay, so part B is the correct option. Okay, is that clear? We move to the question number 14. Okay, the self ignition or pre ignition or auto ignition is desirable for SI engine. So what is self ignition or pre ignition or auto ignition? In SI engine, you know that mixture of fuel and air comes inside, then it is compressed, then with the help of a spark plug, it is ignited. Okay, so this is spark ignition, and diesel it auto ignites. Okay, but this auto ignition can also take place in CI engine. How it can take place? This can take place because there can be some hot regions in the cylinder. Like for example, you can think about something, some particles, some soot particles or something which have been stuck at some location inside the cylinder, and they are very hot, so they can act like a source of ignition. Okay, so that can be one possibility. Okay, so what will happen when you are compressing the air fuel mixture? It is becoming hot and hot, but still a spark plug action has not taken place. But something which was stuck inside the cylinder and it was very hot, and that can act like a source of ignition. Okay, and you will have no control over that. Okay, so that is pre-ignition or self ignition. Okay, so you do not want that. Okay, you want the ignition to be take place just because of spark plug. Okay, so that is not desirable. Okay, so that is called pre-ignition. Okay, there can be some hot spots inside the cylinder, inside the engine, and because of that the auto ignition or pre-ignition can take place. And there is something called knocking basically take place, usually it takes place after the spark plug action. So what happens when the spark plug action has taken place, and the flame will start propagating, and as it is propagating, the in the region behind the flame there will be combustion product. Okay, so in this region, in the dashed region, the combustion has taken place, but here there will be unburnt air fuel mixture. But since the pressure and temperature is continuously increasing, so auto ignition can take place in this region. Okay, there can be some pockets there, there will be auto ignition. Okay, so that is called knocking. Okay, so why knocking take place? Because of uh, auto ignition of unburnt air fuel mixture, because of very high pressure and temperature due to flame propagation. Okay, so there are some different type of ignitions, and we don't want these type of ignitions. We want ignition because of spark plug. Okay, so is it desirable? No, it is not desirable, so it is false. Okay, I hope these things are clear. Okay. So we'll move to the next question if it is there. Okay, it says, in an air standard cycle, it is assumed that real open cycle is changed to closed cycle by assuming that the combustion products exhausted to atmosphere are fed back with the press charge in the intake system. Okay, just try to understand what does it mean. When you study the cycle, closed cycle, so what basically we mean that the working fluid is, it is same. Okay, it is not changing. The same working fluid is going is undergoing different processes: compression, expansion, or whatever, heat addition or heat rejection. Right? Okay. For example, in refrigerators, you have same refrigerant filled inside the coil, and that refrigerant is circulating. So it is not changing again and again. Okay, it is not like you are filling it, and after 2 3 minutes again you are removing it, again filling it. But in engines, you are continuously filling the press air the fresh fuel, and you are throwing out the combustion products. Okay, so the engine cycles, the IC engine cycles, they are open cycles, they are not closed cycles. But air standard cycles that you have studied, the Otto cycle or diesel cycle, they are closed cycle. So this is what is being asked in the question. In air standard cycle, it is assumed that real cycle is changed to closed cycle. Okay, in air standard cycle the closed cycle, but the real cycles, they are not closed cycle. So how this thing it changed from open cycle to closed cycle? So what we assume that whatever combustion products are thrown into the atmosphere, they are again coming inside the, you know, cylinder. Okay, the press charge is coming inside. Okay, so what we assume that the same, you know, working fluid is undergoing different processes. That is what is meant by closed cycle. Okay, so this is the assumption that is made for air standard cycle. Okay, and air standard cycle, anyway, we are not considering the combustion. So whatever we are considering is that air is the only working medium. This is very important. In air standard cycle, we do not consider fuel or fuel air mixture or combustion gases or exhaust gases, nothing, just air. And air is assumed to be an ideal gas with constant properties. Okay, and we also assume that whatever air is going out, the same press air is coming inside. So, okay, in this way, the open cycle is changed to the closed cycle for our analysis. Okay, so again, we will read in the air standard cycle, it is assumed that the real open cycle is changed to closed cycle by assuming that the combustion product, this combustion product is not a very good term for air standard cycles, but anyways, it is written that it is assumption. Uh, it is exhausted to atmosphere. Whatever is exhausted to atmosphere is fed back with the phase charge in the intake system. So this is true. Okay, I hope this is clear. Most of the, you know, power cycles, internal combustion engine related power cycles, they are, you know, open cycles. But the vapor power cycles, they are not they are not open cycle, because the same water circulates. Okay, the same water, it will go inside the turbine, it will go inside the boiler, it will go inside the pump, it will go inside the condenser, the same water. Okay, and the combustion is taking place outside. Okay, outside the boiler. Okay, so the vapor power plants, they are not the internal combustion engines, they are external combustion engines, if you want to say. Okay, and diesel engine or petrol engine or your aircraft jet engines, they are internal combustion engine, because combustion is taking place mm, inside your combustion chamber, and every time you are getting the fresh thing, and you are throwing the waste gases or exhaust gases into the atmosphere. Okay, so if it's clear, then we can move to the next question. Okay, question 16. It says that 1 kilomole of octane C8H18 is burnt with air that contains 20 kilomole of O2 oxygen, as shown in this figure. Assuming the products contain only CO2, H2O, O2, and N2, determine the mole number of each gas in product and air fuel ratio for this combustion process. Okay, why this term assuming is used here? It is used because after combustion, there are many species which are coming out. Okay, for example, in air, there is nitrogen, and nitrogen can react with oxygen, and it can form oxides of nitrogen. Okay, there can be other gases which can also take place in the combustion process. Okay, so I'm just giving you one example, and CO2 is not the only product. Carbon monoxide can be there. Okay, so a lot of products can be there, but it is given in the question that we have to assume that only these are the combustion products. Okay, so based on this information we will proceed. Okay, so what we have C 8H18 plus air. So what is there in air? There is oxygen, and you know what is the ratio of oxygen and nitrogen by volume? There is around 20% oxygen and 80% nitrogen. You must have read this in books. So what does the basically mean is this is by volume. So if you write it by in terms of mass, you can write it as okay. So for every one oxygen there is 3.76 nitrogen. Okay, so this is by mole or by volume, and the 20-80 ratio is by mass. So there is CO2 plus H2O plus O2 and N2, and we don't know how many moles are coming out. So it is given X CO2, Y H2O, Z O2, or W N2, and we what we have 20 kilomole of oxygen. So 20 kilomole of oxygen. Okay. So now you can solve this equation. How? By balancing each species. Species by species I mean basically mean atom. Okay, atom of different elements. Uh, so atoms, number of atoms of all the elements should be conserved. Okay, so for example, if we see the carbon atoms, so on the right hand side there are 8 carbon atoms. On the left hand side there are X carbon atoms. Okay, so X should be 8. Okay, if you balance the carbon atoms, so you will get X is equal to 8. Okay, then what we have hydrogen. On the left side we have how many? 18 18 hydrogen. Okay, on the right hand side we have y into 2 2y hydrogen. So this means y should be equal to 9. Correct. Now if you want to balance oxygen, then on right hand side we have how many? 20 into 2 2 O atoms. So we have 40 oxygen atoms is equal to, on the right hand side you have oxygen in carbon dioxide. How many? 2x plus in H2O y oxygen atoms, and in oxygen itself you have 2Z. Okay, and you have the x value. X is 8, so it will be 2 into 8 plus 9 plus 2Z is equal to 40. Okay, so from here you can calculate what Z. Okay, Z will be equal to 2Z equal to 40 minus 16 minus 9. Okay, it's equal to how much? 15. So Z is equal to 7.5. Okay, and W, nitrogen. So on right hand side we have 20 into 3.6 nitrogen. On right hand side we have 2 W. Okay, so W will be 37.6. No, sorry, 20 into 3.6 is equal to 2W. Okay. So we have 3.37.6. Okay. And correct. There's something wrong. Oh, here it is N2. Okay. So we need to multiply by 2. We will do it again. For N, it will be equal to 20 into 3.6 into 2 is equal to 2 into W. So this 2 will cancel out and W will become how much? 75.2. Okay. So now we have the balanced equation. Okay. So should we write it? Okay, let us write this thing again. We have C8H18 plus 20 O2 plus 2 plus 3.76 into is equal to how many CO2? 8 CO2, right? Plus 9 H2O plus how many CO2? Z 7.5 O2 plus 75.2 N2. Okay. So now we have balanced equation, and what we had to find? We have to find the number of moles of each gas. Okay, so we have found out the number of moles of each gas, and air fuel ratio we have to find. What is the air fuel ratio? Air fuel ratio means mass of air to the mass of fuel. Okay, so mass of air is how much? 20 into 2 into O2. What is the mass of O2? 32, right? And 3.7, how much it was? 76 into 28. So this is air, and mass of fuel we need to find, and mass of fuel will be what it is, C8H18. So for carbon it is 12 and 8 plus 18, right? So we need to calculate this value. Twenty into 2 into 32. Why 2? Why I am writing 2 here? 32 is correct because 32 is for oxygen, plus 3.76 into 28 Okay, divided by 12 into 8 plus 18. So it is coming out to be 24.08. Yes, this is what I am getting. So I have taken just some, approximate values for uh, mass of COH and okay. So you can check in the tables. There you will get more accurate values. But the answer will be very close to this one. Okay, maybe 24.1, 24.2, or maybe 34, 23.9, something like that. Okay, so this is our air fuel ratio. And what else was there? We had to found the number of moles of each gas. Okay, so for carbon dioxide it is 8 moles. For so for water it was 9 moles. For oxygen it was 7.5 moles. For nitrogen it was 75.2 moles. And for air it was how much? 1 for oxygen plus 33.76 into 22, these many moles of air. Okay, please remember this 20 is not the number of moles of air. This 1 of oxygen plus 1 nitrogen. So 4.76 into 20, these are the number of moles of air. Okay, so so sorry, just add the number of moles of oxygen and nitrogen, you will get the number of moles of air. 95.2. Okay. Okay.
Sir, will it be moles or kilomoles?
If this 20 was kilomole, then it will be kilomole. If it was mole, then it will be mole. Okay, here it was kilomole. So sorry. So everything is in kilomole. Okay. This is in kilomole, so everything will be in the kilomole. If it was mole, then everything was in mole.
Sir, I have doubt with that regarding equation. Can you please repeat it? How we got that
Sure, sure,
equation?
sure. Which question?
That equation. How did you get that equation? C8H18 plus 20 O2 plus 3.7
Okay,
is
okay, okay.
empty.
Sure. See, few things we already know and something we don't know. Okay, what we know is that fuel is C8H18, that we know, right? Hello.
Yes, yes, yes.
And O2 plus uh, this 3.76 N2, this we know from the composition of air, right? And it is given that it is burned with 20 kilomole of oxygen. Okay, O2. So that's why we have written 20 mole of O2. Okay, then we are getting these things. And we don't know the exact composition of CO2, H2O, O2, and N2. Okay, that's why we have written X, Y, Z, W, some variables. That's why we are finding the uh, these value of these variables. Now
Okay,
it is
sir.
not
I have
just
doubt
one minute.
regarding that
Yes,
composition of
let
air.
let let me complete. Okay, uh, it is not written that it is complete combustion or incomplete combustion. If it was a complete combustion, then there will be no left oxygen. Okay, if it was a stoichiometric mixture of air and fuel, then Z value will be 0. Okay, Z, and this Z will be 0, right? If it was a stoichiometric mixture, because there will be no leftover oxygen. So since here Z has some positive value, that means there is some extra air. Okay, so we have excess air. Okay, so you can also find the ratio of air fuel mixture when it was stoichiometric and when it is not the stoichiometric, that we call equivalence ratio. Okay, so this is how we balance it. Something we don't know, we assume, and then we find the value of the variables. So now if it is not, if does not answer your question, then please go ahead.
Uh, I
So
just want to know that how that air composition came, that O2 plus 3.76 into. Just doubt regarding that.
okay. See, this is the I mean standard composition of air. You must have studied in your like high school textbook. There are 20% oxygen or 80% nitrogen. Okay, something like that you might have studied. Okay, from there it
Yes,
comes.
yes,
It is
yes.
just huh?
I studied that.
Yes, yes. From there it comes. Okay, we can try. Okay, let us try. Okay, let us say we have 20 and 80. Hello.
Yes, yes, I'm listening.
Okay, let us say it is by mass. Okay, okay, 20 mass of oxygen and 80 mass of nitrogen. Then if you divide by 32, then it will become number of moles of oxygen, and you divide by 28, then it will become number of moles of nitrogen. Okay, now if you take the ratio, then what you will find is, I will just do it by calculator. Okay, 20 by 32, so it is coming 0.625. And if you do 80 by 28, then it is coming 2.85. And if you take the ratio of these things, then I think it should be, we should get that value. Are you getting what I doing? What I am doing? 625 divided by, sorry, 0.625 divided by 2.85. Then it is coming out to be this much. And if you take the ratio of 1 to 3.76, and we are getting the same value. Okay, similar value. So I think I
Okay, sir.
have made him some mistake. Just you should just cross check these values. So it is not exactly 20 or 80. So there is some difference. Okay,
Okay, sir. Thank you, thank you.
but I have a doubt that I should cross check that this 80 by 20 that we have read in our textbook, that is by mass or by moles itself. Okay, because if it is by moles, then we don't need to divide it by this 32 or 20. Okay, what I guess that this 2080 value should be by volume. Okay, not by mass. Okay, so you had a very good question. So it gave me a chance to clarify my own things. But I will encourage you to do it by yourself. It is just a simple mathematics. Okay, you got it. What I mean. Okay,
Okay,
this
sir.
20
I shall
this
check it.
okay, it will be like around 70 79 to 21 or 80 or 20. So most probably it is by volume. Okay, so you don't need to divide it by 32 or 28, but if it is by mass, then you should divide it by this. But this value I remember because most of the time I am doing calculation for combustion, then it is just like a standard value. Okay,
Okay, sir. Thank you. Thank you.
so we have already crossed 2 hours. It is 2 hours a few minutes, so I think we should close here. And one question I left in between, so I will this is a differentiation question. Okay, so you just put all these values in terms of volume, then you convert all these values in terms of compression ratio. Then for maxima, what you do, you differentiate by variable and put it equal to 0. Then whatever r value you will get, that will give you the mm, that will give you the maximum work output, and the corresponding value for compression ratio you have to find. Okay, and the option I will tell you, the correct option is the first one, and you can check it. Okay, maybe you can discuss this in the next session. Okay, I will just cross check this thing, the last part, because it is important. Composition of air. Okay, should we Google this? It is asking for some. Okay, this is by moles. Okay, I'm sorry. This is by moles, and this is understood from this equation itself. Everything we are writing in moles, so it should be in moles, and the volume is proportional to the number of moles. For example, 1 mole of any gas at atmospheric pressure will take up around 22 or 24 liters, right? So this is by moles, and composition of air, 1 mole of O2, 3.76 of N2. Now you can find the percentage of it O2. So what will come out? It will be 1 by 1 plus 3.76. So I will just quickly calculate this thing for you. 1 by 1 plus 3.76. Okay, so it is coming out 21%.
21%.
And right, so nitrogen will be 3.76 divided by 1 plus 3.76, so it should be 79%. Okay, so thank you very much for this question. Okay, so
Thank you,
this
sir.
thing is
Thank you.
by what? Okay, so this 21 or 21 and 79 ratio, this is by moles, or you can say by volume. Okay.
Got it, sir. Got it. Thank you.
Okay, thank you. Okay, so we'll stop here. We will meet in the next session next Tuesday. Thank you.
Thank you, sir.
Thank you. Bye.